What if everything you thought you knew about time was completely wrong? We've all seen movies where heroes jump through decades or change the past with a single-step stories that make us wonder, could it really be possible? From H.G. Wells' classic novel to modern blockbusters like Back to the Future and Interstellar, the idea of traveling through time captures our imagination like almost nothing else. It speaks to something deep within us, the desire to rewrite our mistakes, witness history firsthand, or glimpse the future. But what lies beyond the fiction? What do physicists, philosophers, and futurists really say about bending the fourth dimension? Today, we're setting off on a journey into the unknown as we explore 30 of the most astonishing, perplexing, and downright mind-bending theories about time travel. This isn't just science fiction. We'll be diving into concepts rooted in real science, from Einstein's relativity to quantum mechanics, as well as wilder ideas that stretch the limits of our understanding. We'll ask questions that have puzzled great minds for generations. Can we truly traverse time? Would changing the past unravel reality as we know it? Are we living in a universe where time travel is not just possible, but happening all around us, hidden in plain sight? This video is your invitation to expand your mind and challenge everything you assume about time, cause and effect, and even your own place in the cosmos. Whether you're a curious newcomer or a longtime enthusiast, there's something here to spark your sense of wonder. So settle in, open your imagination, and get ready, because by the end of this exploration, you may never look at time the same way again. And so we arrive at one of the most famous and chilling thought experiments in all of time travel theory, the Grandfather Paradox. Picture this: you build a time machine, set the dial for a date decades before you were born, and travel back to a time when your grandfather was a young man. For reasons only you know, you decide to prevent him from ever meeting your grandmother. Perhaps you inadvertently cause an accident, or maybe you directly intervene. The result is the same. Your grandfather never has children, which means one of your parents is never born, which ultimately means you are never born. But if you were never born, how could you have traveled back in time to set these events into motion in the first place? This is the paradox, a dizzying, self-negating loop of cause and effect that seems to break the very rules of logic. Physicists and philosophers have proposed several fascinating resolutions to this seemingly impossible puzzle. One compelling idea is the concept of a self-consistent timeline, often associated with Novikov's self-consistency principle. This theory suggests that the laws of physics simply will not allow a paradox to occur. Any attempt to change the past would be inevitably thwarted by a seemingly endless series of coincidences and accidents. Your gun might jam as you take aim. You might slip on a banana peel at the crucial moment. The universe, in this view, has a kind of built-in proofreading system that ensures all events remain consistent, making you not an author of a new history, but merely a player who was always part of the original script. Your actions in the past were always what happened, and they always led to the future you came from. Another, perhaps even more mind-expanding, solution comes from the many worlds interpretation of quantum mechanics. This theory proposes that with every decision and every quantum event, the universe splits into multiple branches, creating an infinite tapestry of parallel realities. Under this model, your time travel journey doesn't change your own past. Instead, the moment you arrive in the past and take any action, you create a fork in the road, branching off into a new, parallel universe. In this new timeline, you might succeed in preventing your grandfather's meeting, and thus, in that specific reality, you would never be born. But that's okay, because the original timeline where you were born remains untouched and unchanged. You are essentially a tourist from one universe who has become a permanent resident in another. A universe that now has a history that includes your intervention. This idea transforms time travel from an act of changing history into an act of selecting a new reality altogether. While the grandfather paradox makes us question whether we can change the past, another theory asks an even more fundamental question: does anything truly have an origin? This is the bootstrap paradox, a concept so strange it challenges our very understanding of cause and effect. Imagine a time traveler who is a huge fan of a famous composer, so she travels back to the 1800s to meet him. When she arrives, she discovers the composer has vanished. Desperate to not alter history, she takes the composer's unfinished sheet music, completes it herself using melodies she remembers from the future, and publishes the symphony under his name. The music becomes a legendary, timeless classic. But here's the twist: where did the music actually come from? The composer in the past never wrote it. The time traveler only knew it because she had learned it in her future, which was based on the past she herself created. The information, the music itself, has no point of origin. It simply exists, trapped in an infinite loop where it creates itself. This paradox isn't confined to music. Think of an inventor who receives a detailed blueprint from an older version of himself, a design for a revolutionary machine. He then uses that blueprint to build the very same machine. Years later, as an old man, he uses the machine to travel back in time and give the blueprint to his younger self. The knowledge of how to build the machine was never invented by anyone. It was just perpetually handed down from the future to the past in a closed circle with no beginning. The bootstrap name comes from the idea of pulling yourself up by your own bootstraps, an impossible feat where the effect is also the cause. There is no initial spark, no first cause that set the loop into motion. It simply is. This idea completely unravels our linear perception of causality, the comfortable notion that event A causes event B. In a bootstrap scenario, there is no event A. The universe would contain objects or information that are literally uncaused. Philosophers argue this creates a universe that is, in a way, irrational or self-referential. Physicists, however, often see it as a potential feature of certain solutions to Einstein's equations, like closed time-like curves, where the geometry of space-time could allow for such loops to exist without violating any physical laws. The paradox doesn't create a universe-destroying contradiction like the grandfather paradox might. Instead, it presents a reality that is consistent but utterly inexplicable, a stable loop where the question of "where did this come from?" is a question that has no answer. If the idea of parallel universes and paradox loops feels overwhelming, the next theory offers a much stricter, and some would say more elegant, solution. Enter the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov. This principle is built on a beautifully simple yet profound assertion: anything a time traveler does in the past must have already been a part of that past. There is no changing history because your journey and your actions were always woven into the fabric of events. In this view, the universe is a single, immutable timeline, and it is fundamentally impossible to create a paradox. The laws of physics themselves would conspire to prevent any inconsistencies from ever occurring. Think back to the grandfather paradox. Under Novikov's rule, your attempt to interfere would be doomed from the start. Perhaps you travel back with the intention of stopping your grandfather, but at the crucial moment, you suddenly recognize a family heirloom he's carrying, a pocket watch you were told was lost, and you hesitate. Or maybe you slip on a wet patch of ground, your shot goes wide, and you only graze his arm. That minor injury could even be the very story he later tells your grandmother, the event that brings them closer together. Your violent action, intended to erase him, instead becomes the catalyst for their relationship. You didn't change history, you fulfilled it. Every single action you take in the past was always a part of that past, leading inexorably to the future from which you came. You are not an outside force crashing into history. You are a cog that was always turning in the grand machine of time. This concept of a single, predetermined timeline inevitably leads us to a monumental question about free will. If our future selves could travel back and their actions were always part of our past, does that mean our entire lives are already scripted? The Novikov principle suggests that our perception of choice might be an illusion. Every decision you believe you are making freely, what to eat for breakfast, which job to take, whether to build a time machine, was already a fixed point in the timeline. You were always going to make those choices. This introduces a powerful form of destiny, not guided by fate or gods, but by the immutable laws of physics. The universe, in this model, is a completely self-consistent story where the ending is already written, and we are merely reading our way through it. This stands in stark contrast to theories like the many worlds interpretation, where many worlds offers infinite branches and endless possibilities. Novikov's universe offers only one unchangeable path. It's the difference between an endlessly expanding tree and a single, unbreakable circle. One theory celebrates possibility and choice, creating a new reality with every decision. The other offers a universe of profound order, where paradoxes are not solved by branching away, but are made impossible from the outset. One is a chaotic, creative multiverse. The other is a perfectly edited, final cut of a film where no scene can ever be left on the cutting room floor. Both are compelling answers to the same terrifying question, yet they paint two entirely different pictures of reality itself. But if a single, fixed timeline feels too constricting, the many worlds interpretation of quantum mechanics throws the doors of possibility wide open. This theory, first proposed by physicist Hugh Everett in the 1950s, suggests that our universe is just one branch on an infinitely expanding tree of reality. Every time a quantum event occurs with more than one possible outcome, every choice you make, every particle that could spin up or down, the entire universe splits. One version continues where the particle spun up, and a new, equally real universe branches off where it spun down. This isn't a rare event. It's happening constantly, at every moment, creating a mind-boggling multiverse of parallel existences where every conceivable possibility is realized somewhere. When we apply this concept to time travel, the famous paradoxes that plague other theories simply melt away. Remember the Grandfather paradox. In the many worlds model, it ceases to be a paradox at all. If you travel back in time to a point before your birth, you are not traveling back into your own past timeline. Instead, your arrival itself is a quantum event that causes the universe to branch. You step into a new, parallel universe that is nearly identical to your original history up until the moment you appeared. In this new branch, you are free to act without fear of erasing yourself. You could prevent that version of your grandfather from having children, and it would have absolutely no effect on the original timeline you came from. In that new reality, you would never be born, but the you standing there is a visitor from another world. A living impossibility in that universe, but a permanent fixture in its new history. You haven't changed the past, you've simply emigrated to a different version of it. This view transforms the time traveler from a potential history wrecker into an explorer of the multiverse. Your time machine is less a vehicle for moving through years and more a device for hopping between adjacent branches of reality. Every action you take in the past doesn't rewrite history, but instead creates a new fork in the road, a new timeline that diverges based on your intervention. The implications are staggering. It suggests there are universes where the Roman Empire never fell, where dinosaurs still roam the earth, and where you made every different choice you ever pondered. There is a version of reality where you are a famous musician, another where you live on a different continent, and infinite others where the laws of physics themselves are completely alien. This infinite proliferation of realities also introduces profound questions about identity and consequence. If every decision spawns a new universe, then the version of you in this current moment is just one of countless copies. The choices you make don't change your fate. They simply determine which branch of the multiverse this particular version of you gets to experience. It can feel both liberating and deeply isolating. On one hand, every mistake you've ever made has been corrected in another reality. On the other, it means we are all ultimately alone on our individual branch, forever separated from the infinite other versions of ourselves and our loved ones by the unforgivable mathematics of probability. The many worlds interpretation doesn't just allow for time travel. It paints a picture of a cosmos of infinite beginnings, infinite endings, and infinite stories all unfolding simultaneously. While the many worlds theory opens up a vast multiverse of possibilities, another concept rooted firmly in Einstein's own work suggests that time travel could be achievable right here in our own universe, without needing to jump to another reality. This idea revolves around something known as closed time-like curves. In the framework of general relativity, space-time isn't just a static stage. It's a dynamic fabric that can be warped and curved by mass and energy. A closed time-like curve, or CTC, is a path through this warped space-time that loops back on itself, allowing an object to return to its own starting point in both space and time. It's essentially a physical pathway that could, in theory, be followed to travel into your own past. The mathematics behind this isn't science fiction. It comes directly from solutions to Einstein's field equations. One of the first people to discover this was the brilliant logician and mathematician Kurt Gödel. In the 1940s, Gödel, who was a close friend of Einstein's at the Institute for Advanced Study, found a solution to the equations that described a rotating universe. In this bizarre cosmos, the entire universe is spinning, and this rotation twists the fabric of spacetime so severely that following certain paths would allow you to travel back in time. While we don't live in a universe that appears to rotate in that way, Gödel's work was a monumental proof of principle. It showed that time travel wasn't automatically forbidden by relativity. The laws of physics, as we understand them, could accommodate it. So how could we actually create one of these paths? One compelling proposal involves a massive, infinitely long cylinder rotating at an incredible speed. This idea was developed by physicist Frank Tipler. In theory, such a massive rotating object would drag spacetime around with it, an effect known as frame dragging. If the cylinder were dense enough and spun fast enough, it could twist spacetime into a helix. By carefully navigating around this cosmic whirlpool, a spacecraft could find itself on a closed time-like curve, effectively circling back to a point in time before it began its journey. The practical hurdles are, of course, astronomical. Building an infinitely long, ultra-dense cylinder is far beyond our current, or perhaps any civilization's capabilities, but the fact that the physics allows it is what captivates theorists. Another, perhaps more famous, proposed vehicle for closed time-like curves is the wormhole. Often pictured as a tunnel or shortcut connecting two distant points in spacetime, a wormhole could also connect two different times. If one mouth of the wormhole was moved at a significant fraction of the speed of light or placed near an intense gravitational field like a black hole, time would dilate for that end relative to the other. This would create a time difference between the two mouths. Walking into one end would mean exiting the other not just in a different place, but in a different time. If the tunnel could be stabilized, a huge challenge as wormholes are thought to be incredibly unstable, it would effectively form a stable, traversable closed time-like curve, a permanent gateway to the past or future. This all sounds thrilling, but it comes with a host of profound problems that physicists are still grappling with. The most significant is perhaps the issue of causality violation and those pesky paradoxes we discussed earlier. If closed time-like curves exist, they seem to invite the same grandfather paradox problems. However, some physicists, like Igor Novikov, argue that the self-consistency principle would apply here as well. The universe would naturally prevent any paradox from occurring, meaning you could travel on a closed time-like curve, but you would be physically incapable of changing any event in a way that creates an inconsistency. Your journey into the past was always part of that past. Other theorists propose that the extreme energy conditions needed to create a CTC might be impossible to achieve without triggering effects from quantum mechanics that would destroy the curve before a paradox could form. The very act of trying to create a time machine might be what prevents it from ever working, acting as a sort of cosmic censorship that protects the timeline from logical contradictions. But if building a wormhole time machine seems fantastically difficult, one theoretical physicist proposed a design that is, in its own way, even more staggering in its scale. This is the concept of the Tipler cylinder, named after Frank Tipler, who worked out the detailed mathematics in the 1970s. The idea builds directly on Einstein's theory of general relativity, which tells us that massive objects warp the fabric of spacetime, and that rotation can further twist and drag that fabric. Tipler's incredible proposal was that an enormous cylinder, made of an unbelievably dense material and spinning at a significant fraction of the speed of light, could warp spacetime around it so severely that it would form a closed time-like curve. By flying a spaceship in a precise, corkscrew path around this rotating cosmic pillar, you could effectively travel back in time. The sheer scale of this proposed machine is almost impossible to comprehend. First, the cylinder isn't just large, it must be infinitely long. While physicists often use the concept of infinity to simplify calculations, building something of infinite length is, of course, a physical impossibility. Even a cylinder of finite but extraordinary length would present challenges far beyond any engineering feat humanity has ever conceived. Second, the cylinder must be made of a material of unimaginable density, something far beyond the strength of neutron star matter, to avoid being torn apart by its own incredible rotational forces. It would need to be perfectly rigid and incredibly massive, spinning at near light speed. The energy required to set such an object spinning, let alone construct it in the first place, would dwarf the total energy output of every star in a galaxy. This leads to why most physicists, including Tipler himself, view this as a mathematical curiosity rather than a practical blueprint. The theory is sound within the framework of general relativity, the equations permit it, but the assumptions needed are so extreme that they exist in a realm of pure theory. We have no known material in the universe that could possess the necessary strength and density. The forces involved would be so titanic that any known substance would be instantly vaporized or crushed into a singularity. Furthermore, the requirement for infinite length is a major sticking point. It suggests that the conditions for time travel might only be possible in a universe with fundamentally different physical boundaries than our own. So, while the Tipler cylinder remains a fascinating thought experiment that demonstrates the flexibility of Einstein's equations, it is widely considered a practical dead end. It shows us that the laws of physics might not explicitly forbid time travel to the past, but they seem to guard the secret very closely, requiring conditions so extreme that they might as well be impossible. It serves as a perfect example of the chasm that can exist between a mathematical solution and a physical reality. A reminder that some doors in the universe, even if they are not locked, may be far too heavy for anyone to ever open. While the Tipler cylinder presents a challenge of almost unimaginable scale, another theoretical time machine offers a slightly more familiar, though no less incredible, concept: the traversable wormhole. Popularized in countless science fiction stories, a wormhole is often depicted as a tunnel or shortcut through the fabric of space-time, connecting two distant locations in an instant. But according to the rigorous work of theoretical physicists like Kip Thorne, a wormhole could do much more than just cut across space. It could also connect different moments in time, becoming a genuine time machine. The basic principle relies on Einstein's theory of general relativity, which tells us that gravity is the curvature of spacetime. A wormhole is a solution to Einstein's equations that describes a bridge between 2 points, a kind of cosmic subway tunnel with 2 entrances, or mouths. For this tunnel to be traversable, meaning a human could theoretically pass through it without being instantly crushed, it must be held open against the immense gravitational forces that would otherwise snap it shut. This is where the concept of exotic matter enters the picture. Unlike normal matter, which always has positive energy density and exerts attractive gravity, exotic matter would have negative energy density, generating a form of anti-gravity or repulsion. This strange substance would act as a kind of structural scaffolding, propping the wormhole's throat open and making passage possible. But how does a spatial shortcut become a time machine? The answer involves manipulating the two mouths of the wormhole relative to each other. Imagine you have a traversable wormhole. You leave one mouth, mouth A, safely on Earth. You then take the other mouth, mouth B, and embark on a journey on a spaceship capable of traveling at a significant fraction of the speed of light. Due to the effects of time dilation from Einstein's special relativity, time will pass more slowly for the moving mouth and the spaceship crew than it does for the stationary mouth back on Earth. If you travel for what feels like 1 year at near light speed and then return to Earth, you might find that 10 years have passed for everyone there. This is the standard twin paradox, but here's the crucial twist. Because the wormhole connects the 2 points in spacetime instantly, the time difference is now locked in between the two mouths. When you return, mouth B has aged only 1 year, while mouth A on Earth has aged 10 years. If you were to immediately step into mouth A on Earth, you would instantly exit from mouth B, which is now sitting right next to you on your spaceship. But you would be emerging 9 years in the past relative to Earth's calendar. The wormhole has become a time machine leading directly to a moment 9 years earlier. Anyone could now step into the stationary mouth on Earth and journey back to that point in the past. The further you travel or the faster you go with the movable mouth, the greater the time difference you can create, potentially allowing for travel millions of years into the past or future. The work of physicist Kip Thorne and his colleagues in the 1980s brought this idea from the realm of pure speculation into a subject of serious scientific inquiry, famously sparked by a request from Carl Sagan to devise a plausible method of interstellar travel for his novel Contact. Thorne's calculations showed that while the physics permitted such a structure, the engineering requirements were staggering. The exotic matter needed to stabilize the wormhole isn't just rare, it might not even exist in the necessary quantities. We see hints of negative energy in certain quantum effects, like the Casimir effect, but harnessing enough of it to hold open a macroscopic tunnel is a challenge that may forever remain in the realm of theory. Furthermore, some calculations suggest that the very act of turning a wormhole into a time machine might trigger a violent feedback loop of radiation, potentially destroying the tunnel the moment it becomes useful for time travel, acting as another form of cosmic censorship protecting the timeline from paradox. Yet another gateway through time might be woven into the very fabric of the cosmos itself, from the very first moments after the Big Bang. These are cosmic strings, hypothetical fissures in spacetime that are thought to be left over from the universe's incredibly hot and dense infancy. Picture the early universe cooling and undergoing a phase transition, much like water freezing into ice. As water freezes, cracks and fissures can form in the ice. In a similar way, as the universe cooled and expanded, immense cracks in the structure of spacetime itself may have formed, one-dimensional defects of almost unimaginable density. A cosmic string would be narrower than a proton, but a single inch of it could have the mass of Mount Everest. This incredible density means a cosmic string would warp the spacetime around it with a gravitational field of staggering power. The potential for time travel emerges not from one string, but from the interaction of two. If two such cosmic strings were to pass by each other at a significant fraction of the speed of light, their combined gravitational fields could twist the fabric of spacetime into a knot so tight that it forms a closed time-like curve. The mathematics, first explored by physicist J. Richard Gott in the 1990s, shows that the precise geometry of their paths could create a loop in time. It wouldn't be a machine you could build or control, but a natural, albeit incredibly rare, phenomenon in the universe. A temporary gateway to the past that appears and then vanishes as the strings continue on their way. You wouldn't need exotic matter or infinite cylinders. You would just need to find and navigate this fleeting gravitational whirlpool. The challenge, of course, is that these strings remain entirely theoretical. We have no confirmed observational evidence that they exist. Detecting something so infinitesimally thin yet so massive is a monumental task for cosmologists. One promising method involves looking for their ghostly imprint on the oldest light in the universe, the cosmic microwave background radiation. The immense gravity of a cosmic string would subtly distort the light passing by it, creating telltale double images of distant galaxies or specific patterns in the temperature of the background radiation. Another method involves searching for their effect on the timing of incredibly precise cosmic clocks, pulsars. The gravitational wave from a passing cosmic string would create a unique signature in the otherwise steady rhythm of these spinning neutron stars. So far, these searches have come up empty, but the hunt continues, as proving the existence of cosmic strings would not only open a door to time travel, but also provide a direct window into the universe's very first moments. But if cosmic strings represent a cosmic scale possibility, the next theory shrinks the entire problem down to the most fundamental level of reality. Welcome to the bizarre and counterintuitive world of quantum time travel. At the quantum scale, the rules are entirely different from the classical physics that govern our everyday lives. Particles can be in two places at once. Information can seem to travel instantaneously, and cause and effect don't always follow a neat, linear order. It's within this strange domain that physicists are exploring some of the most plausible models for sending information, if not people, backwards in time. One of the most fascinating proposals involves a phenomenon we're already familiar with: quantum entanglement. You've likely heard of this spooky action at a distance, where two particles become linked in such a way that measuring the state of one instantly determines the state of the other, no matter how far apart they are. This connection seems to defy the speed of light, but it doesn't allow for communication. Now, some theorists propose that this spooky connection might not just be across space, but across time as well. The idea of temporal entanglement suggests that particles could be entangled not just over distance, but across different moments. A particle in the present could be linked to a particle in the past, their fates intertwined across time itself. If this is true, manipulating a particle now could theoretically influence its partner in the past, opening a channel for quantum information to effectively travel backwards in time. This leads to an even more mind-bending concept known as post-selection. Imagine you want to send a single bit of quantum information back in time. In a standard quantum computer, you run a calculation and you get a result. But in a post-selected quantum computer, you would set up your experiment to only accept a specific, desired outcome. You essentially tell the universe, "I will only consider this experiment a success if the result is X." The wild implication is that by imposing this condition on the future, you could influence the probability of events that led to that result in the past. It's as if the future outcome is reaching back and guiding the initial setup. This doesn't create a grandfather paradox because the process is probabilistic. It only works for outcomes that were possible to begin with, but it strongly biases the timeline toward that specific result. You're not sending a message to the past in a conventional sense. You are forcing the entire timeline to be consistent with the future you have chosen. While building a full-scale time machine using these principles remains a distant dream, scientists have already begun simulating these effects in the lab. In 2010, a team of researchers led by Seth Lloyd at MIT proposed a quantum experiment to simulate a particle traveling back in time and interacting with its younger self. They didn't actually bend time. Instead, They used a quantum system to mimic the mathematics that would describe such a journey. By carefully entangling photons and using a complex series of measurements, they were able to create a scenario where a photon state was altered in a way that was mathematically equivalent to it having traveled back in time and changed its own past. The results were consistent with the Novikov self-consistency principle. The photon's journey was always consistent, and no paradoxes arose. It was a simulation, not the real thing, but it provided a stunning proof of concept that the laws of quantum mechanics might indeed support this kind of consistent time travel on a microscopic scale. Another groundbreaking experiment in 2014 took this even further. A team at the University of Queensland in Australia performed a simulation that effectively closed the loop on the famous Grandfather paradox itself. They used photons to represent a time traveler and a separate quantum system to represent the past. In their experiment, the time traveler photon was sent through a wormhole-like loop to interact with and try to destroy its earlier self. Just as Novikov predicted, the laws of quantum mechanics ensured a consistent outcome every single time. The time traveler photon always interacted in a way that prevented a paradox from ever occurring. It was never able to completely erase itself. The universe, even in this tiny simulated form, found a way to preserve its own logical consistency. These experiments are like flight simulators for time travel, allowing us to test the physics of causality in a controlled environment, and strongly suggesting that the quantum world might be far more flexible with time than our classical intuition would ever allow. All of these concepts, from cosmic strings to quantum loops, push the boundaries of our imagination, but there is one form of time travel that is not just theoretical. It is a proven, measurable fact of our universe, happening all around us right now. This is the phenomenon of time dilation, a direct prediction from Einstein's theory of special relativity that tells us time does not tick at the same universal rate for everyone. The faster you move through space, the slower you move through time relative to someone who is standing still. This isn't a philosophical idea or a quirk of perception. It is a fundamental property of spacetime itself, and it provides us with a clear, achievable method for traveling into the future. The most famous illustration of this is the twin paradox. Imagine a pair of identical twins. One is an intrepid astronaut who boards a spacecraft capable of traveling at 90% the speed of light. The other stays safely here on Earth. The astronaut embarks on a journey to a distant star and back. From the perspective of the twin on Earth, this round trip might take, say, 20 years. They age 2 decades, growing older, waiting for their siblings' return. But for the astronaut twin, because they are moving at such an incredible velocity, time itself is stretched out. Their clocks tick more slowly. Their biological processes decelerate. For them, the entire journey might only take, for example, 5 years. When the spacecraft finally lands back on Earth, the astronaut steps out. They have only aged 5 years, while their Earth-bound sibling has aged 20. The spacefaring twin has effectively jumped 15 years into the Earth's future. They have become a time traveler. This incredible effect has been confirmed not just in thought experiments, but in real-world science with astonishing precision. In one of the most famous confirmations, scientists in 1971 used extremely accurate atomic clocks. They placed one clock on a commercial jet aircraft and flew it around the world, while an identical clock remained perfectly synchronized on the ground. After the flight, the two clocks were compared. The clock that had been traveling on the fast-moving plane was measurably behind the stationary clock by a few hundred nanoseconds. The difference was tiny, but it was there, exactly as Einstein's equations had predicted. Time for the moving clock had literally passed more slowly. Today, this isn't just a laboratory curiosity. It's a critical engineering consideration. The Global Positioning System, or GPS, that guides our cars and phones relies on a network of satellites orbiting Earth at high speeds. Because of time dilation, The atomic clocks on these satellites run slower than clocks on the ground. If the incredibly complex software running the GPS network did not constantly correct for this relativistic effect, the entire system would become useless, accumulating errors of several miles within a single day. Our ability to navigate relies on our acceptance that time travel to the future is a real, physical phenomenon. This form of time travel, however, comes with a significant catch. It's a one-way ticket. Special relativity allows us to jump forward into the future, but it does not provide a path back to the past. You could use an ultra-fast spacecraft to travel 10,000 years into Earth's future, but there would be no return journey to your original time. You would be a permanent visitor in a new era. The energy requirements to achieve a significant time jump are also staggering. To experience just a few years of time dilation while centuries pass on Earth, you would need to sustain velocities incredibly close to the speed of light, a feat that demands energy levels far beyond our current capabilities. Yet, the principle stands firm, etched into the fundamental laws of physics. The universe has already provided us with a recipe for time travel. It is now a question of whether we can ever build an engine powerful enough to follow it. But special relativity is only half the story Einstein gave us. While motion alone can send us racing into the future, his theory of general relativity introduces an even more powerful, and perhaps more profound, time machine: gravity itself. This is the concept of gravitational time dilation, and it tells us that time doesn't just slow down when you move fast. It also slows down when you stand deep within a gravitational well. The stronger the gravity, the slower the clock ticks. This means that by simply getting closer to an incredibly massive object, like a black hole, you could embark on a one-way journey into the distant future. To understand why, picture spacetime not as a blank stage, but as a flexible rubber sheet. A massive object, like a planet or a star, creates a depression in this sheet. Now, imagine time as a pattern of lines on that sheet. As the sheet curves downward into the gravity well, the lines of time get closer together. For someone down in that well, time is literally stretched, causing their seconds to pass more slowly compared to someone up on the flat, high ground far away from the gravity source. You, living on the surface of Earth, are already experiencing this effect compared to someone floating in deep space. Your time is passing ever so slightly slower because you are deeper in Earth's gravitational field. The difference is infinitesimal, but it is real and measurable. One of the most elegant confirmations of this came from the Pound-Ribka experiment at Harvard University in 1959. Physicists Robert Pound and Glenn Ribka used a brilliant method to detect this tiny effect right here on Earth. They exploited a phenomenon called the Mersbauer effect to create an incredibly precise gamma-ray source and detector. They placed the source at the bottom of a tower and the detector at the top, a distance of just 22.5 meters. According to general relativity, the photons climbing out of Earth's gravity well should lose a tiny amount of energy, a gravitational redshift. Pound and Ribka measured this shift with breathtaking accuracy, confirming that time indeed runs faster at the top of the tower than at the bottom. The experiment was a stunning success, providing direct, terrestrial proof that gravity literally shapes the flow of time. Now, amplify that effect from a university tower to a cosmic scale. Consider a supermassive black hole, an object with gravity so intense that not even light can escape its pull. The gravitational time dilation near such an object would be extreme. Imagine a team of intrepid astronauts on a mission to orbit just outside the event horizon of a black hole. For every single hour they experience in that intense gravity, years, centuries, or even millennia might pass for everyone back on Earth. They could orbit for what feels like a few days, and upon returning to their home planet, find that they have leaped thousands of years into its future. They wouldn't feel like they were moving in slow motion. Their hearts would beat at a normal rate, their conversations would flow normally, but their local time would be out of sync with the rest of the universe, decoupled from the flow of time on Earth. This presents a fascinating and perhaps tragic implication for future deep space exploration. Any civilization attempting interstellar travel would have to contend with this effect as a fundamental fact of navigation. A crew visiting a region of strong gravity wouldn't just be risking physical danger. They would be making the conscious choice to sever their connection to the timeline of their homeworld. They might return to find their culture transformed, their loved ones long gone, and their planet unrecognizable. Their journey would be a one-way trip into the future, making them the ultimate archaeologists, discovering the ruins of their own civilization. This isn't just theoretical. Our GPS satellites have to account for both forms of time dilation. The clocks on these satellites are both moving fast relative to the ground and in a weaker gravitational field. The combined effect means their clocks run faster than those on Earth. And if engineers didn't constantly correct for this, the entire system would fail within minutes. Our daily reliance on technology is a constant, silent testament to the fact that gravity is a master sculptor of time itself. This brings us to a theory that might be the most philosophically jarring of them all, one that completely upends our most basic experience of reality, the block universe theory. Also known as Eternalism, this concept suggests that our intuitive sense of time passing, the feeling that the past is gone, the present is happening, and the future is yet to be is nothing more than a powerful illusion. Instead, past, present, and future all exist simultaneously, fixed forever in a vast, four-dimensional structure. In this model, time is not a river flowing from a source to the sea. It is more like a loaf of bread, where every slice, from the crust to the end, exists at once. We are simply conscious beings moving through this static block, experiencing one slice at a time in a steady sequence we call now. This idea finds its roots in Einstein's own work. After the death of his close friend Michel Besso, Einstein wrote a letter to Besso's family, offering a profound consolation that revealed his personal view of time. He said, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion." For Einstein, the reality described by his equations of relativity was a four-dimensional spacetime continuum, a block where every event, from the Big Bang to the heat death of the universe, has a fixed location. Your birth, your reading of this sentence, and every event in your future are all equally real. They are just located at different coordinates in the space-time block. This view has profound and unsettling implications for our understanding of free will and identity. If the future already exists in a fixed, unchangeable state, then the choices we believe we are making are not truly choices at all. We are simply following a path that is already laid out, discovering our lives like a reader turning the pages of a book that has already been written. This is a form of determinism far more absolute than any proposed by philosophers. It isn't that your actions are predetermined by prior causes. It's that your entire timeline, from beginning to end, is just there. You are a four-dimensional worm woven through the block of space-time, and your sensation of making a decision is simply your consciousness encountering a crossroads that was always there. Many modern physicists and philosophers find this view compelling because it elegantly resolves the paradoxes of time travel. If the block universe is real, then there is no such thing as changing the past. A time traveler journeying to a previous era was always a part of that era's space-time coordinates. The events we would call a paradox are simply the complex, fixed geometry of the four-dimensional world. You were always in the background of your grandfather's wedding photo. Your future self was always the one who gave you the blueprints for the time machine. The universe is not a story being written. It is a completed sculpture, and we are merely tracing its contours with the flashlight of our consciousness. This perspective can feel both terrifyingly constricting and strangely comforting, offering a cosmos of perfect, immutable order where every moment of joy and every instance of sorrow is eternally preserved. Now, let's turn to a concept that twists the very idea of free will into a perfect, inescapable loop: the predestination paradox. This theory presents a world where every attempt to change history doesn't just fail, but actively creates the very event the traveler hoped to prevent. Imagine a person who travels back in time to stop a terrible disaster, only to discover that their own actions in the past are the precise, indispensable cause of that disaster occurring in the first place. They didn't alter the timeline, they became the reason it unfolded exactly as it always had. This is the essence of predestination, a closed causal loop where the future influences the past in a way that makes the timeline completely self-consistent and unchangeable. This paradox is brilliantly illustrated in countless stories. One of the most famous examples comes from the original Terminator film. A soldier from the future, Kyle Reese, is sent back in time to protect Sarah Connor from a lethal android assassin. In the process of fulfilling his mission, he and Sarah fall in love, and she becomes pregnant with his child. That child, John Connor, grows up to be the leader of the human resistance, who eventually sends Kyle Reese back in time to protect his own mother. Without Kyle's journey into the past, John Connor would never have been born. The entire chain of events is a perfect circle with no beginning and no end. The cause is the effect, and the effect is the cause. The attempt to change the future ensured its own existence. On a more personal and tragic scale, consider the ancient Greek myth of Oedipus. An oracle prophesies that a king's son will grow up to kill his father and marry his mother. In a desperate attempt to avoid this fate, the king orders the infant to be killed, but the child is saved and raised by another family. Years later, Oedipus, unaware of his true parentage, does indeed kill his biological father in a chance encounter on the road, and later marries the widow who is his mother. The frantic effort to cheat destiny became the very mechanism that delivered it. While not a time travel story in the technological sense, it is the ultimate philosophical exploration of a predestination paradox, showing how the fear of a future can actively manufacture it. This idea forces us to confront deep questions about fate and determinism. If our future selves can travel back, and their actions were always part of our past, does that mean our entire lives are preordained? The predestination paradox suggests a universe that is not just consistent, but scripted. Your life is not a series of choices leading to an unknown conclusion. It is a fixed story where every event is locked in place, and your perception of making decisions is merely the experience of reading the next line. This presents a chilling form of destiny, not guided by gods or magic, but by the immutable, mathematical laws of physics themselves. The universe, in this view, is a single, uneditable film, and we are both the audience and the actors, experiencing a plot that was finished long before we hit play. This stands in stark contrast to the liberating, if chaotic, possibilities of the many worlds interpretation. In a multiverse, every choice creates a new branch, offering infinite versions of reality. But in a predestined, single-timeline universe, there is only one version. There are no alternate realities where things turned out differently. Every heartbreak, every triumph, and every seemingly random accident was not random at all. It was a necessary step in a chain of causality that loops back on itself with perfect, inescapable logic. This can feel constricting, robbing us of our sense of agency. Yet, it can also be perversely comforting, suggesting that there are no true mistakes, only events that were always meant to unfold exactly as they did. In a predestined world, you are exactly where you were always supposed to be, forever playing your part in a story much larger than yourself. Yet this vision of infinite possibilities also raises profound questions about identity and consequence. If every decision spawns a new reality, then the version of you reading this now is just one of countless copies living out every conceivable variation of your life. The choices you make don't change your fate, They simply determine which branch of the multiverse this particular version of you gets to experience. This realization can feel both liberating and strangely isolating. While it means there's a universe where you achieved every dream and avoided every mistake, it also means we are all ultimately alone on our individual branches, forever separated from the infinite other versions of ourselves and our loved ones by the unbridgeable mathematics of probability. The multiverse model doesn't just allow for time travel, it paints a picture of a cosmos teeming with infinite beginnings, infinite endings, and infinite stories all unfolding simultaneously across the vast tapestry of reality. But for all these tantalizing theories and thought experiments, one of the greatest scientific minds of our time believed the universe itself would never allow it. This is the chronology protection conjecture, proposed by Stephen Hawking. After deeply considering the implications of closed time-like curves and time machines, Hawking essentially declared that nature would have a zero-tolerance policy for time travel to the past. He famously quipped, "If time travel is possible, where are the tourists from the future?" His conjecture is a bold assertion that the laws of physics must contain a yet undiscovered mechanism that prevents backwards time travel, thereby protecting the timeline from paradoxes and preserving a clear, consistent history. Hawking wasn't just making a philosophical argument, he was looking for a physical law. He theorized that any attempt to create a time machine would trigger a catastrophic feedback loop of energy that would destroy the apparatus before it could become operational. One proposed mechanism involves quantum effects. Imagine trying to stabilize a wormhole time machine with exotic matter. Hawking and others calculated that the moment you tried to create the time machine, the energy fluctuations within the wormhole would become infinite. In the quantum realm, empty space isn't truly empty. It's a seething foam of virtual particles constantly popping in and out of existence. These are known as vacuum fluctuations. The theory suggests that as you twist space-time into a time loop, these quantum fluctuations would get caught in the loop, traveling back and forth and building upon themselves with each pass. Their energy would amplify exponentially in a runaway feedback effect, becoming infinite in a fraction of a second, and either destroying the wormhole or creating a singularity that would shut down the time travel corridor. Another potential guardian of chronology is the phenomenon of radiation. In the presence of a closed time-like curve, the radiation field itself could become unstable. Hawking's own work on black hole radiation plays a role here. Calculations show that the energy density of quantum fields would be likely to diverge or blow up to infinity on the edge of the time travel region. It wouldn't be a dramatic explosion in the classical sense, but a profound failure of the very physics that describes the situation. The equations of general relativity would break down, and quantum gravity effects, which we don't yet understand, would take over, presumably preventing the paradox from ever occurring. The universe, in this view, has a kind of cosmic immune system. The moment a paradox infection tries to take hold, the laws of physics rally to produce a fever so high it sterilizes the wound in spacetime, killing the time machine in its crib. This idea that nature actively forbids time travel is compelling because it aligns with our observed reality. We don't see time travelers, and our most advanced physics has yet to find a loophole that isn't guarded by an insurmountable physical barrier. Hawking's conjecture is essentially an argument from common sense, backed by the full weight of theoretical physics. It suggests that the logical consistency of the universe is not an accident but a fundamental feature, enforced by physical law. The arrow of time may be an irrevocable one-way street, not because we lack imagination or engineering skill, but because the cosmos is built to keep it that way. It is the universe's ultimate firewall, protecting causality itself from the logical viruses that time travelers could introduce. If the mind-bending concepts of predestination and quantum loops have you questioning the very nature of cause and effect, then prepare to have your understanding of time turned completely inside out. We now venture into the subatomic realm, where the rules of our everyday reality are not just broken, they are rewritten. This is the domain of quantum retrocausality, a theory that proposes the future can literally reach back and influence the past. In this bizarre world, the comfortable, linear progression of cause, then, effect is not a fundamental law, but merely a common habit of the larger world we inhabit. At the heart of this idea is the notion that the arrow of time, which always seems to point forward, might be a two-way street at the quantum level. One of the most compelling demonstrations of this comes from a modern update to a classic thought experiment, the quantum delayed choice experiment. Imagine a single photon approaching a beam splitter, a device that can either let it pass straight through or reflect it, creating two possible paths. Now, downstream, we place a second device that can either be a detector, to see which path the photon took, or a second beam splitter that recombines the paths. If we choose to measure which path the photon took, it behaves like a single particle, having chosen one definite route. But if we choose to recombine the paths, the photon behaves like a wave, having traveled both paths simultaneously and interfering with itself. The astonishing part is this: we can make this choice after the photon has already passed the first beam splitter. It's as if the photon's decision on how to behave, as a particle or a wave, is made retroactively based on a measurement decision we haven't even made yet. The future measurement appears to be reaching backwards in time to tell the particle how to behave in the past. This isn't just an abstract idea. It has been tested and confirmed in laboratories around the world. In a landmark 2007 experiment, scientists sent photons on a long journey through optical fibers, making the delay between the photon's passage at the first beam splitter and the experimenter's choice at the second apparatus a significant fraction of a second. The result was always the same. The photon's behavior was consistently correlated with the future choice. It didn't matter when the decision was made. The particle's past state was irrevocably linked to the future measurement setup. This doesn't mean we can send a message to the past, but it strongly suggests that at the quantum level, the categories of cause and effect are not fixed in time. The universe seems to be arranging events in a globally consistent way, where the future can play a role in shaping the past, just as the past shapes the future. So how could this possibly work without creating paradoxes? One interpretation is that the flow of time itself is an emergent property, not a fundamental one. In the block universe model we discussed earlier, where all of time exists at once, retrocausality isn't a violation of physics because there is no privileged now. From a God's eye view outside of time, the experimenter's choice and the photon's behavior are simply two events with a specific relationship. Our human perception, which forces us to experience these events in a sequence, creates the illusion that the later event is mysteriously affecting the earlier one. In reality, both are fixed parts of the four-dimensional whole, and their connection is just a feature of that whole's geometry. This has staggering implications for our understanding of reality. It suggests that the universe operates not like a chain of dominoes falling in a line, but more like a completed crossword puzzle, where the meaning of one clue is informed by the letters of another, regardless of which one you look at first. Your actions in the present aren't just building the future, they could also be finalizing the past. The universe we observe may be the result of a delicate negotiation between what has happened and what will happen, a cosmic consistency that transcends our everyday experience of time. While this doesn't allow for a time machine to send you back to meet your grandfather, it does open the door to a universe where time is far more fluid, interconnected, and mysterious than we ever dared to dream. Now, let's journey into one of the most groundbreaking and unusual realms of modern physics, where scientists are not just studying time, but creating entirely new phases of matter that behave in ways once thought impossible. This is the world of time crystals. Unlike the familiar crystals of salt or quartz, which have atoms arranged in a repeating pattern in space, a time crystal has a structure that repeats in time. It's a system that oscillates or ticks forever without any energy input, effectively breaking what physicists call time translation symmetry. This means that, just as a regular crystal looks different if you shift your perspective in space, a time crystal looks different if you shift your perspective in time, but it does so in its ground state, its lowest energy state. It's like finding a clock that winds itself, ticking perpetually without ever running down. The concept was first proposed by Nobel laureate Frank Wilczek in 2012, and it initially seemed to flirt with violating the laws of thermodynamics. The first law concerns the conservation of energy, and the second law, the increase of entropy, tells us that systems tend to run down and become disordered. A perpetual motion machine is impossible. Yet, a time crystal doesn't actually create or output energy. It simply uses no net energy to maintain its perpetual oscillation. It's not a machine doing work. It's a stable, quantum system trapped in a never-ending loop, like an electron forever orbiting a nucleus without radiating energy away. This strange behavior arises from a phenomenon known as many-body localization, where quantum interference prevents a system from reaching equilibrium, locking it into a persistent, rhythmic pattern. The potential applications for studying the nature of time itself are profound. Because a time crystal is a quantum system with a built-in, ultra-stable rhythm, it could act as a perfect natural clock, far more precise than any atomic clock we have today. But more intriguingly for time travel theory, it provides a tiny laboratory-scale model of a closed time-like curve. The oscillating pattern of a time crystal is a stable, self-repeating time loop. By creating and observing these systems, physicists can study how causality and time symmetry work in a controlled environment, offering insights into whether larger, more complex time loops could ever be stable in our universe. It's a sandbox for testing the physics of time. This isn't just theoretical speculation. In recent years, there have been stunning experimental breakthroughs. In 2017, two separate teams, one at the University of Maryland and another at Harvard, successfully created time crystals in the lab using vastly different setups. The Maryland team used a chain of ytterbium atoms, while the Harvard team used diamonds with dense impurities. Both systems were kicked into their perpetual motion with an initial laser pulse, and then they continued to oscillate at a fraction of the driving frequency, a clear signature of a time crystalline phase. Even more remarkably, in 2021, researchers observed time crystals interacting with each other, a crucial step towards understanding how these systems could be used for quantum information processing. These developments open a door to a future where we might not just ponder time travel, but harness the principles of time crystals to build devices that manipulate time in fundamentally new ways. Imagine a quantum computer whose qubits are protected from decoherence by being locked into the stable rhythm of a time crystal, or a network of these crystals acting as a flawless timing system for navigating the solar system. While we are not building a DeLorean, we are creating matter that dances to a rhythm all its own, giving us a tangible, physical system to explore the deepest mysteries of time, causality, and perhaps one day, the very loops that could make time travel a reality. While the Tipler cylinder and cosmic strings rely on massive structures, another proposal offers a sleeker, though no less speculative, vision for crossing the cosmos and time itself. This is the Alcubierre warp drive, a concept that sounds like it was pulled straight from science fiction, but was actually born from a rigorous examination of Einstein's field equations. In 1994, Mexican physicist Miguel Alcubierre asked a simple yet profound question: could general relativity allow for faster-than-light travel without actually breaking the universal speed limit locally? His stunning answer was yes, by not moving through space but by moving space itself. The principle is elegant. Imagine space-time as a treadmill belt. Instead of trying to run forward on the moving belt faster than the belt itself is moving, an impossible feat, you could simply pull the belt behind you while rolling out a new section in front. Alcubierre's solution describes a spacecraft nestled inside a flat region of spacetime called a warp bubble. Behind the ship, spacetime is expanded, pushing the point of origin far away. In front of the ship, spacetime is contracted, pulling the destination closer. The ship itself remains motionless inside this bubble, not accelerating in the traditional sense, and thus avoiding the relativistic effects that would crush a human body. The bubble itself, however, can then move through the warped spacetime at effectively any speed, including speeds greater than that of light, because it is spacetime itself that is moving, not the object within it. The time travel implications emerge directly from the tenets of special relativity. If you can travel from Earth to a distant star faster than a beam of light could make the journey, you are effectively outrunning your own light cone. From certain reference frames, your arrival at the star could occur before your departure from Earth. You would have created a closed time-like curve. Imagine a scenario where you warp to a star system 4 light-years away and back. From the perspective of everyone on Earth, your round trip might take a decade. But because you traveled faster than light, you might return after only a year of your personal time, arriving back on Earth 9 years before the light from your departure even reaches that distant star. You haven't just traveled through space, you've leapt backwards in Earth's timeline, becoming a visitor from its future. The monumental hurdle, as with so many of these ideas, is the energy requirement. To create the extreme curvature of spacetime needed for the warp bubble, Alcubierre's original calculations called for astronomical amounts of energy, potentially equivalent to the mass energy of Jupiter or even an entire star. Furthermore, the geometry of the bubble requires something even more elusive: exotic matter with negative energy density. This isn't just rare antimatter, it's a theoretical substance that would have to exhibit negative mass, creating a repulsive gravitational effect to push spacetime apart behind the ship and pull it together in front. While tiny amounts of negative energy might be possible through quantum effects like the Casimir vacuum, assembling the planet-sized quantities needed for a macroscopic warp drive seems far beyond any foreseeable technology. Later research has offered a glimmer of hope. Calculations by physicists like Chris van den Broek and others have suggested that by tweaking the geometry of the warp bubble, the energy requirements could be drastically reduced, perhaps down to the mass energy of something like the Voyager 1 spacecraft. While still an immense amount of energy, this brings the concept from the realm of pure fantasy into the territory of a theoretical possibility. NASA Eagleworks Laboratory has even conducted small-scale experiments to try and detect the microscopic warping of spacetime, though no definitive evidence has been found. The Alcubierre drive remains a beautiful mathematical possibility, a testament to the incredible flexibility of Einstein's universe, and a dream that one day, the vast distances between the stars might be bridged not by Chinese letter journeys, but by bending the very stage upon which the drama of the cosmos is played. But if the Alcubierre drive represents a potential engine for leaping across spacetime, our journey now takes us inward, to the very smallest scales of reality where the rules of time itself are written in probability and paradox. We arrive at a theory that asks if the universe's most fundamental layer might hold the key to navigating time's greatest contradictions. This is the realm of temporal paradoxes in quantum mechanics, a domain where the bizarre principles that govern particles could offer elegant solutions to the problems that break our classical brains. At the heart of quantum mechanics lies the concept of superposition, the idea that a particle does not have a definite property until it is measured. Until that moment, it exists in a cloud of all possible states simultaneously. This is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box is both alive and dead until someone looks inside. Now, apply this quantum weirdness to a time traveler facing the grandfather paradox. In a classical view, the traveler either succeeds or fails in their mission, creating a logical inconsistency. But through a quantum lens, the time traveler exists in a superposition of states. At the moment of the attempted intervention, the traveler is both someone who has killed their grandfather and someone who has failed, and the entire universe is in a superposition of both timelines. It is only when the event is observed, when the consequences become manifest in the timeline, that this quantum wave function collapses into one definite outcome. This leads to two radical and unsettling ideas: quantum suicide and quantum immortality. Imagine a time traveler who sets up a quantum experiment linked to their own survival. Perhaps they build a gun aimed at themselves that is triggered by a radioactive atom, which has a 50% chance of decaying in the next minute. In the many worlds interpretation, the universe splits. In one branch, the atom decays and the gun fires. In another, it does not and the traveler lives. But from the perspective of the traveler's consciousness, they can only experience the branches in which they are alive. They would subjectively never experience death. Now, scale this up to a time travel paradox. A traveler who attempts an action that could erase their own existence might, from their own subjective viewpoint, only ever experience the timelines where they miraculously survive. They might slip on that banana peel, or their gun might jam, not because of a classical self-consistency principle, but because all the branches where they succeed and vanish are simply branches they cannot experience. Their continued existence is a selection effect of their own consciousness navigating the multiverse. So how does a quantum system actually handle these contradictory timelines without collapsing into nonsense? The answer may lie in quantum decoherence. This is the process by which a quantum system loses its superposition and becomes firmly settled into one state due to interactions with its environment. Think of it like this. It's easy for a single electron to be in two places at once because it's incredibly isolated. But it's impossible for a cat or a human time traveler to be in a superposition of states for long because they are constantly bumping into trillions of air molecules, photons of light, and other particles. Each interaction effectively measures the system, forcing it to choose a state. In the context of a paradox, a time traveler's actions would immediately interact with the vast number of particles in the environment, causing the quantum wave function of the event to decohere almost instantly. The universe wouldn't linger in a fuzzy state of both/and. It would rapidly resolve into one consistent timeline, most likely one that follows a path of least resistance, avoiding the logical inconsistency altogether. This provides a potential physical mechanism for Novikov's self-consistency principle. The laws of quantum mechanics themselves, through decoherence, would act as the editor that ensures only self-consistent events can become classical reality. Any action that would create a true paradox would result in a quantum state that is incredibly unstable and prone to rapid decoherence into a stable, consistent outcome. The time traveler isn't protected by fate, but by the fundamental quantum physics of measurement and interaction. Their free will isn't violated. It's simply that the outcomes of their choices are constrained by the requirement of logical consistency, which is enforced by the same quantum laws that govern every other particle in the universe. In this view, paradoxes are not just prevented. They are physically impossible states that the universe is fundamentally incapable of sustaining. This brings us to a profound puzzle that questions the very nature of existence and origin, a concept known as the ontological paradox. The word ontology deals with the nature of being and reality itself, and this paradox strikes at the heart of what it means for something to be created. It describes a scenario where an object, a piece of information, or even a person is sent back in time, becoming the cause of its own existence in the future. The item has no discernible point of origin. It simply exists in a closed, self-contained loop, forever becoming the reason for its own being. It is a universe where the question, "Where did this come from?" is a question that literally has no answer. One of the most compelling ways to visualize this is through the story of an inventor and a revolutionary machine. Imagine a young, struggling inventor toiling away in his workshop, unable to crack the design of a world-changing device. One day, an elderly stranger appears and hands him a set of flawless, complex blueprints. The young inventor uses these plans to construct the machine, which becomes a monumental success, making him famous and wealthy. Decades later, now an old man himself, he finally builds a time machine. He realizes that to ensure his own success, he must travel back in time and deliver the blueprints to his younger self. So he does, creating a perfect loop. The blueprints were never actually invented by anyone. The knowledge to build the machine did not spring from any mind or any creative process. It was always just there, circulating endlessly through time. The information is its own cause and its own effect, a closed circle of creation with no beginning. This idea completely unravels our most basic understanding of causality, the comfortable and intuitive rule that every event must have a cause that came before it. In our everyday world, we see a straight line. A composer writes a symphony, an artist paints a masterpiece, a scientist derives a new equation. There is a clear point of creation. The ontological paradox shatters this linearity, replacing it with a loop where the effect precedes the cause. The symphony exists because it was brought from the future, and it was brought from the future because it existed. This creates a universe that is logically consistent. There is no contradiction, but it is also fundamentally inexplicable. It presents a reality where some things might not have been created at all, but have always been part of the timeline's immutable structure. We see this paradox explored brilliantly in science fiction. In the film 12 Monkeys, the protagonist's haunting childhood memory of witnessing a man get shot at an airport is in fact his own future death. The memory has no origin other than the event it predicts. Perhaps the most famous example is the iconic scene in The Terminator where the remains of the original destroyed T-800 android are used by Cyberdyne Systems to reverse engineer the technology that will eventually create Skynet. Skynet then sends a Terminator back in time to protect its own creation, ensuring the very research that leads to its existence. The advanced technology, the key to Skynet's rise, was not invented by anyone. It was discovered in a wreckage from a future war, a wreckage that would not exist if the technology had not been discovered. The loop is perfectly closed and utterly origin-less. From a philosophical standpoint, this paradox forces us to confront what creation really means. Does something need a creator? If a time loop can bring an object into existence without a point of origin, does that object have any less reality? It challenges notions of intellectual property and even art. Could a famous novel or painting have no true author, simply appearing from nowhere as a gift from the future? It suggests that our universe might contain uncaused causes, things that bootstrap themselves into reality without a prime mover, existing outside the chain of cause and effect that we believe governs everything. Physicists see a potential home for such loops in certain solutions to Einstein's equations of general relativity, particularly in what are known as closed time-like curves. The mathematics allows for paths that loop back on themselves, and within these loops, an ontological paradox could reside quite comfortably. There would be no law of physics broken, no energy created or destroyed. The object in the loop would just be there. However, this doesn't make the paradox any less dizzying. It presents a cosmos that can be rationally described but not rationally explained. A universe that contains mysteries which are, by their very nature, forever beyond our understanding. We are left with the unsettling yet awe-inspiring realization that some of the foundations of our reality might be built not on a first cause, but on an eternal, self-sustaining mystery. But perhaps the most direct, and certainly the most perilous, pathway through time might not require building a machine at all, but simply finding the courage to dive into one of the universe's most terrifying phenomena. This brings us to the theory of time travel via rotating black holes. Not all black holes are the simple, destructive pits we often imagine. While a standard Schwarzschild black hole crushes everything into an infinitely dense point of no return, a rotating black hole, described by the Kerr solution to Einstein's equations, is a far more complex and strangely structured object. Its rotation flattens it into a dynamic whirlpool of space-time, and within its violent depths, the mathematics suggests there might be a way through. At the heart of a Kerr black hole lies not a point singularity, but a ring singularity, a whirling, donut-shaped loop of unimaginable density. This crucial difference changes everything. Because the singularity is a ring rather than a point, the gravitational forces at its center might not be infinite in all directions. The complex geometry of warped spacetime around this ring could, in theory, allow for paths that avoid the crushing density altogether. These are not magic escape routes. They are specific, hair-thin trajectories predicted by the equations of general relativity. If a spacecraft could navigate with impossible precision, it might pass through the ring itself. And what lies on the other side? The mathematics opens up a dizzying array of possibilities, a different region of our own universe, a parallel universe, or even a gateway to a different time entirely. The ring singularity could act less like a wall and more like a cosmic turnstile. The potential pathway through this cosmic maelstrom is known as an Einstein-Rosen bridge, more popularly called a wormhole. The intense rotational energy of the Kerr black hole could theoretically keep the throat of this wormhole propped open, creating a stable tunnel. The exit of this tunnel wouldn't necessarily lead to the same point in spacetime where you entered. Due to the effects of extreme time dilation and the twisted geometry, exiting could place you in a different time, millions of years in the past or future, or in a completely different universe altogether. The black hole becomes less a dead end and more a chaotic, natural interchange on the spacetime freeway. However, the dangers involved are so extreme that this method borders on pure suicide. First, there is the accretion disk, a frenzied whirlpool of superheated gas and dust spinning around the black hole at near light speed. Navigating through this celestial blender of radiation and debris would be a feat in itself. Then comes the even greater challenge, tidal forces. As you approach the black hole, the difference in gravity between your head and your feet would be immense. For a small black hole, this spaghettification would stretch and tear any object apart long before it reached the ring singularity. A supermassive Kerr black hole would have gentler tidal forces at its event horizon, perhaps allowing a spacecraft to cross without being instantly shredded. But the margins for error would be infinitesimally small. Finally, there is the problem of stability. Most theoretical models suggest that the wormhole inside a Kerr black hole would be incredibly unstable. The mere presence of any matter or energy, like a spacecraft attempting to pass through, could cause the tunnel to collapse instantaneously into a singularity, sealing your fate. Even if the tunnel held, there is no guarantee you could control where or when you would emerge. You might be flung into the heart of a star, the void of intergalactic space, or a universe with completely different physical constants. The journey would be the ultimate gamble, a one-way trip into the absolute unknown with odds of success so vanishingly small that it remains, for now, one of physics' most thrilling and terrifying thought experiments. Yet if navigating a black hole feels like a cosmic dice roll, the next theory turns its gaze inward, suggesting that the ultimate time machine might not be a device we build, but the very consciousness that observes it. This is the many minds interpretation, a provocative and deeply philosophical offshoot of quantum mechanics that proposes a startling idea. When the universe branches, it is not reality itself that splits, but our perception of it. In this view, every possible outcome of a quantum event does occur. but they all happen within a single, overarching reality. The branching is not a physical process creating parallel worlds, but a psychological one occurring within the minds of observers. Your consciousness becomes the lens through which a single, complex universe is perceived in a multitude of different ways. Apply this to the experience of time travel, and the paradoxes begin to dissolve in a uniquely personal way. Imagine a time traveler setting out to change a past event. In the many worlds view, their actions create a new branch of reality. But in the many minds view, their journey doesn't create a new universe at all. Instead, their consciousness simply decouples from the timeline where the event was unchanged, and becomes aligned with a new, subjective experience of a timeline where it was changed. The external, objective reality remains one consistent whole, containing all possible histories simultaneously. The traveler isn't hopping between worlds. Their mind is shifting its focus to a different thread within the vast, woven tapestry of a single reality. They subjectively experience having altered the past, while the original, unaltered past remains just as real, simply observed by a different state of their own consciousness. This approach elegantly sidesteps the thorniest issues of paradox. Consider the grandfather paradox once more. A traveler who attempts to prevent their own birth would, from their subjective viewpoint, succeed. They would experience a reality where their grandfather died young, and they were never born. But according to the many minds' interpretation, this is not a logical contradiction. The objective universe still contains the consistent history where the grandfather lived and the traveler was born. The traveler's consciousness has simply entered a state of awareness that is consistent with a history where they do not exist. A seemingly impossible feat that this theory allows by separating conscious experience from a single, linear timeline. There is no paradox because both sequences of events are true components of the one real universe. The traveler's mind has just journeyed from perceiving one part to perceiving another. The philosophical implications of this are profound and more than a little dizzying. It places consciousness not as a passive observer of a predetermined reality, but as an active participant that navigates a sea of possibilities. Your sense of identity becomes fluid. The you reading this is just one of many possible conscious states of your broader mind, each experiencing a different outcome of the quantum events that define your life. This suggests a form of subjective time travel that is always available to us. Every decision we make could be seen as our consciousness selecting a path through the garden of forking paths, not by changing the garden itself, but by choosing which flower to stop and smell. We are all, in a sense, time travelers within our own minds, constantly experiencing one potential history while countless others equally real. This view can be both liberating and isolating. It liberates us from the fear of paradox, as the universe's logical consistency is never broken. Yet it can feel isolating, suggesting that our most personal experiences are just one narrow slice of a much grander, incomprehensible whole. Your triumphs and tragedies are utterly real to you, but they are not the only version of your story that exists. The many minds interpretation doesn't offer a starship to the past, but it does offer a radical new perspective on our place within time, proposing that the journey through history might be the most intimate trip we ever take, a voyage not of the body, but of the conscious self through the infinite possibilities that reality has to offer. Yet as we probe the bizarre connections that quantum entanglement might forge across time, we must also confront the monumental challenges this idea poses to the very pillars of modern physics. The principle of causality, the unshakable rule that cause must precede effect, is a cornerstone of our understanding of the universe. If information can truly be sent instantaneously into the past, it opens the door to the same paradoxes that haunt other time travel theories. Imagine receiving a message from your future self warning of a terrible event, which you then avoid. But if you avoid the event, what prompted your future self to send the warning in the first place? This creates a maddening loop with no origin. Beyond the logical puzzles, quantum retrocausality appears to directly challenge Einstein's theory of relativity, which establishes the speed of light as the ultimate cosmic speed limit and enforces a strict temporal order for events that can be causally connected. Allowing influence to flow backwards in time seems to undermine the very foundation of a rational, predictable universe. Physicists are not content to leave this as a philosophical debate. They are designing ingenious experiments to test the limits of quantum non-locality and temporal order. One groundbreaking approach is the quantum delayed choice experiment, which we touched on earlier. In a stunning 2017 implementation, scientists in China used satellites to perform a delayed choice experiment over a record-breaking distance, entangling photons and making measurement decisions after those photons had already been detected. The results consistently showed that the photon's behavior was correlated with the future choice, reinforcing the bizarre possibility that the quantum world does not respect a rigid arrow of time. Even more recently, experiments have begun testing causal inequalities, mathematical constraints that any universe obeying a standard cause and effect relationship must satisfy. By manipulating entangled particles, researchers are essentially trying to force the universe to break these rules, to see if effects can be measured before their causes under very specific quantum conditions. So far, the universe has stubbornly maintained its causal consistency, but the very act of testing these boundaries is revealing a reality far more fluid and strange than we ever imagined. The true promise of this research may lie not in building a telephone to the past, but in revolutionizing our understanding of the universe's most fundamental workings. If quantum entanglement does indeed involve a form of temporal connection, it could be the key to unifying the two great pillars of modern physics, quantum mechanics and general relativity. These two theories have remained stubbornly separate, describing the universe of the very small and the universe of the very large with different rules. The point where they meet, such as in the singularity of a black hole, is where our physics breaks down. By exploring how quantum particles behave when the flow of time itself is warped by gravity, scientists hope to find a common language. Experiments are now being proposed that would place entangled particles in states of superposition not just in space, but in time, by subjecting them to different gravitational potentials. Observing how their entanglement holds could provide the first experimental clues toward a theory of quantum gravity, a monumental step toward understanding the cosmos on its most fundamental level. This brings us to a philosophical perspective that, in many ways, provides the ultimate foundation for all these physical theories. It's called Eternalism, and it's the profound idea that time itself is a dimension, much like the three dimensions of space. In this view, the past, present, and future are not ephemeral or transient, they all exist simultaneously and permanently. Think of the entirety of space-time as a vast, four-dimensional block where every event, from the Big Bang to the distant heat death of the universe, has its fixed coordinates. Your birth, your reading of this sentence, and every moment of your future are all equally real. They are simply located at different addresses within this grand, unchanging structure. This is why it's often called the block universe theory. To grasp this, imagine a DVD movie. The entire film, the opening credits, the climax, the final scene, is all present on the disc at once. When you hit play, the laser doesn't create new scenes. It simply illuminates one part of the disc after another, creating for the viewer a subjective experience of a story unfolding. In the block universe, our consciousness is that laser. We don't experience all of time at once. We move through it in a linear sequence, perceiving one frame at a time as the now. But this doesn't mean the other frames don't exist. The past is not gone. It's just a part of the block we are no longer scanning. The future is not unrealized. It's a part we haven't scanned yet. From this perspective, time travel is not about changing the past or creating the future. but simply about moving your point of consciousness to a different set of coordinates within the static block, much like moving through space. This stands in stark contrast to a more intuitive view called presentism. Presentism argues that only the current moment is real. The past is gone, a collection of memories and records, and the future is pure potentiality, a realm of possibilities that do not yet exist. In this model, time is a river flowing from a source we cannot see to a sea we cannot reach, and we are perpetually caught on the ever-moving crest of the wave called the present. Presentism feels natural because it matches our direct, subjective experience. We remember the past and anticipate the future, but we only ever directly interact with the present. However, this view runs into serious conflict with modern physics, specifically Einstein's theory of relativity. Eternalism, on the other hand, finds a beautiful and natural home within Einstein's framework. His theory of special relativity shattered the notion of a universal now. It showed that whether two events occur at the same time depends entirely on the observer's frame of reference. What is the present moment for you on Earth could be a mix of past and future for an astronaut traveling at near light speed past Alpha Centauri. There is no privileged cosmic clock that defines the present for everyone in the universe. Relativity forces us to treat time as a dimension interwoven with space, not as a separate, flowing entity. The block universe model embraces this fully, stating that since there is no absolute present, we must accept that all moments are equally valid and real. The flow of time is an illusion, a necessary artifact of our conscious perception within the block. The implications of eternalism for time travel are both liberating and deeply unsettling. It dissolves the most feared paradoxes. The grandfather paradox cannot occur because your journey to the past was always an event located within the block. You were always present at that moment in your grandfather's youth. Your actions there were always a part of the cause and effect chain that led to your own birth and your eventual decision to build a time machine. The universe is not a story being written, it is a completed book. We are not the authors, but the readers discovering the narrative page by page. A time traveler is simply a reader who chooses to skip ahead or flip back to a different chapter. But the text on those pages was always there, immutable and fixed. This view can feel deterministic, even fatalistic. If the future already exists in a concrete, unchangeable state, it challenges our most deeply held beliefs about free will and choice. Are we truly making decisions, or are we merely following a path that is already laid out, discovering a life that has, in a sense, already been lived? Proponents of eternalism argue that our experience of making choices is no less real. The block contains the entire, complex tapestry of cause and effect, including your process of deliberation and the decision you ultimately make. Your free will is the mechanism by which your consciousness navigates the fixed paths of the block. You are still you, making choices. It's just that the outcomes of those choices are as permanent and real as the choices themselves. Ultimately, eternalism offers a radical but coherent vision of reality, one that is deeply supported by our best physical theories. It transforms time travel from a fantastical violation of natural law into a conceptually simple, if technologically daunting, form of navigation. We already move freely through the three dimensions of space. Eternalism suggests that moving through the fourth dimension of time is not fundamentally different. The challenge isn't bending the laws of physics, but overcoming the limitations of our perception to see the universe not as a series of fleeting moments, but as the magnificent, static, and complete four-dimensional sculpture it truly is. But if navigating the four-dimensional block of eternalism feels abstract, our next journey takes us into a realm with even more dimensions, a lot more. We now venture into the dizzying landscape of string theory, a framework that proposes the fundamental building blocks of the universe are not point-like particles, but unimaginably tiny, vibrating strings. To make the mathematics of these vibrations work consistently, String theory requires something extraordinary: the existence of extra spatial dimensions beyond the three we experience. While we can't perceive these dimensions directly, they could be compactified or curled up at a scale trillions of times smaller than an atom. It is within this complex, higher dimensional arena that some physicists see a potential new pathway for time travel. The key might lie in how these extra dimensions interact with the fabric of spacetime itself. In certain versions of string theory, our entire universe could be a three-dimensional brane, short for membrane, a vast surface floating within a higher dimensional bulk. Think of our cosmos as a single, impossibly thin slice of bread within a much larger loaf. This opens up a breathtaking possibility. If other branes exist parallel to our own, they could represent entirely separate universes with their own physical laws and histories. More importantly for a time traveler, moving through the bulk could allow for shortcuts not just through space, but through time. A journey that would take millions of years within our brain might be a short hop if you could only find a way to dip into the higher dimensional bulk and re-emerge at a different point in our spacetime. This concept of branes provides a fresh perspective on wormholes. In Einstein's general relativity, a wormhole is a tunnel through our four-dimensional spacetime. But in string theory, a wormhole might be better understood as a bridge connecting two different branes, or two different points on the same brane through the bulk. The geometry of these higher dimensions could potentially allow for the creation of stable, traversable wormholes in a way that is impossible in our familiar four dimensions. By manipulating the vibrations of strings, which dictate everything from mass to force charges, we might one day learn to pinch a region of our brain and connect it to another, creating a gateway that links not just two places, but two times. However, it is crucial to emphasize the profoundly speculative nature of these ideas. String theory itself, for all its mathematical elegance, remains a work in progress. It has yet to make a single testable prediction that can be verified through experiment, which places it firmly in the realm of theoretical physics. The energies required to probe the scale of strings or to manipulate extra dimensions are astronomically beyond our reach, perhaps requiring a particle accelerator the size of a galaxy. Furthermore, the theory isn't a single unified idea but a collection of related models, and it's not clear which version, if any, describes our actual universe. The concepts of time travel within it are even more tentative, representing intriguing possibilities rather than concrete blueprints. They show us how the laws of physics might permit such journeys in a universe with more dimensions than we can see, but they do not tell us if our universe is actually one of them. For now, time travel in string theory remains a beautiful and compelling thought experiment, a testament to the power of human imagination to explore the furthest reaches of logical possibility. Now, let's shift our focus from the cosmic scale of black holes and extra dimensions to the incredibly small, where the act of observation itself might hold the key to manipulating time. This is the quantum Zeno effect, a bizarre and counterintuitive phenomenon where a watched pot not only never boils, it never even gets warm. Named after the ancient Greek philosopher Zeno of Elea and his paradoxes about motion, this quantum principle suggests that by repeatedly and rapidly measuring a quantum system, you can effectively freeze it in its current state, preventing it from evolving or changing. It's a concept that transforms the observer from a passive witness into an active participant with the power to influence the very flow of events. To understand how this works, imagine a radioactive atom that has a 50% chance of decaying within a certain period. In the strange world of quantum mechanics, this atom exists in a superposition, a blurred state of being both decayed and not decayed. This fuzzy state will eventually collapse into one definite outcome, either a decayed or stable atom. However, the quantum Zeno effect proposes that if you continuously measure the atom to see if it has decayed, you repeatedly collapse its wave function back to the not decayed starting point. Each measurement essentially resets the quantum clock. If these measurements are done quickly enough, the atom is never given the opportunity to evolve into its decayed state. You have, through observation alone, stopped time for that atom, locking it in a perpetual state of potential. This isn't just a thought experiment. It has been demonstrated in laboratories around the world. One of the most famous confirmations came in 1990, when a team at the National Institute of Standards and Technology used a group of around 5,000 beryllium ions trapped by magnetic fields. These ions can be in a ground state or an excited state. The researchers used laser pulses to repeatedly measure whether the ions were in the excited state. By zapping them with these observation pulses at a rapid rate, they were able to dramatically suppress the natural evolution of the system. The ions were effectively frozen in their initial state, their quantum evolution halted by the constant probing light. It was a direct and dramatic validation that observation has a tangible, physical effect on reality. So, what does repeatedly watching an atom have to do with time travel? The connection lies in the concept of time itself being a product of change. If no change occurs, has any time actually passed for that system? By suspending the evolution of a quantum state, the quantum Zeno effect creates a form of localized time dilation, a tiny bubble where time appears to stand still relative to the outside world. While this is a far cry from a time machine, it opens the door to speculative applications for time stasis. Imagine a future technology that could use this principle on a macroscopic scale, perhaps to perfectly preserve something incredibly delicate, like a living organ for transplant or a quantum computer's fragile state of superposition. By constantly observing it with a precisely tuned field, you could theoretically place it in a state of suspended animation, halting all degenerative processes indefinitely. The leap from freezing a single atom to freezing a complex object like a human is, of course, monumental. The sheer number of quantum states in a macroscopic object is unimaginably vast, and the energy and precision required to continuously measure them all would be beyond any foreseeable technology. Furthermore, the act of measurement in quantum mechanics often involves interacting with the system, which typically means adding energy to it, the opposite of what you'd want for perfect preservation. However, the principle stands as a stunning example of how our understanding of quantum mechanics continues to blur the line between the observer and the observed, suggesting that our consciousness and our instruments might play a far more active role in shaping the flow of time than we ever previously believed. What if the most powerful time machine wasn't a physical device at all, but something we all carry within us, our own consciousness? This idea pushes beyond the realms of physics and into the mysterious territories of the mind, suggesting that time travel might be an internal journey rather than an external one. For centuries, cultures around the world have recounted experiences that seem to defy linear time. People report vivid visions of events yet to come, a phenomenon known as precognition. Others describe moments of retrocognition, where they suddenly feel immersed in a historical event as if they were truly there, experiencing sights, sounds, and emotions from another era with startling clarity. These aren't stories of machines or wormholes. They are accounts of the human mind apparently traversing the timeline through means we are only beginning to understand. Consider the common experience of déjà vu, that eerie sensation that you've lived a moment before. While often dismissed as a neurological glitch, some researchers and theorists propose it could be a fleeting glimpse of time non-linearity, a brief overlap where a future memory brushes against the present. More dramatic are cases of spontaneous precognitive dreams. There are countless documented instances where individuals dreamt of specific, unexpected events, like a plane crash or a natural disaster, only to witness them unfold in reality days later. These aren't vague premonitions. They are often hyper-detailed, containing information the dreamer could not possibly have known through normal means. The experience is so profound that it can permanently alter a person's perception of reality, leaving them to wonder if the future is somehow already written and accessible. The concept of psychic time travel takes this even further. Proponents of remote viewing, a practice developed in Cold War-era programs like Stargate Project, claim that trained individuals can use their minds to perceive distant locations, and crucially, different times. The theoretical basis often hinges on the idea that consciousness is not localized to the brain or the present moment. Instead, it might be a fundamental aspect of the universe, a field that exists outside of space-time, allowing a trained mind to tune in to any point in the past or future. In this view, the mind doesn't travel through time. It simply shifts its focus, much like turning the dial on a radio to pick up a different station. The information is already out there, and consciousness is the receiver. Naturally, these ideas face intense skepticism from the mainstream scientific community. The primary criticism is a lack of reproducible, controlled evidence under rigorous laboratory conditions. Many alleged cases of precognition can be explained by confirmation bias, where people remember the hits and forget the far more numerous misses. Coincidence and the brain's incredible ability to pattern match after the fact also offer strong, non-supernatural explanations. Cognitive scientists point out that our memory is not a perfect recorder. It is a reconstructive process, easily influenced by suggestion and emotion. A powerful feeling of having been there in the past could be a compelling fabrication of the brain, not a genuine temporal journey. Despite the skepticism, the persistence and global nature of these experiences keep the debate alive. Modern research into quantum mind theories, or the ORCH or model proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, offers a potential, though highly speculative, bridge. They suggest that quantum processes within the brain's neurons could potentially allow consciousness to interact with the fundamental spacetime geometry at a very small scale. If consciousness has a quantum component, and if quantum physics truly allows for temporal non-locality, as some interpretations suggest, then perhaps these experiences are not mere illusions but rare and uncontrolled glimpses into a more fluid nature of time that our conscious minds are ordinarily filtered from perceiving. This doesn't prove psychic time travel, but it opens a door to a universe where such a thing might not be outright impossible, just extraordinarily difficult to measure and control. Whether a profound mystery of human potential or a complex trick of the human brain, the idea of consciousness-based time travel challenges us to consider that the greatest frontiers we have to explore may not be among the stars, but within the depths of our own awareness. This brings us to a theory that connects the possibility of time travel directly to our own existence and our observations of the universe. This is the application of the anthropic principle, a fascinating and sometimes controversial line of reasoning that suggests the fundamental constants of our universe are the way they are because, if they were any different, we wouldn't be here to observe them. In the context of time travel, this principle raises a profound and deeply puzzling question. If traveling to the past were truly possible, why does our timeline appear completely devoid of any obvious visitors from the future? The eerie silence of the chrononauts is a mystery that echoes the famous Fermi paradox, which asks, if the universe is so vast and old, where is everybody? We must now ask, if time is so traversable, where are all the time tourists? One compelling explanation is that the absence of evidence is, in fact, evidence of absence. The anthropic principle suggests a sobering possibility. The laws of physics that govern our particular universe, or our local region of a multiverse, might simply forbid time travel to the past. These laws are fine-tuned in such a way that allows for the emergence of stars, planets, and ultimately, conscious life like us. But that same fine-tuning might include a built-in chronology protection mechanism, as Stephen Hawking proposed. We don't see time travelers because the physics of our cosmic neighborhood makes their arrival an impossibility. We exist in a universe where the logical consistency of causality is protected, and that very protection might be a prerequisite for the stable, long-lasting conditions needed for life to evolve. In this view, we are living in a universe that is inherently safe from paradox, and our observation of a traveler-free history is a direct consequence of that safety. But perhaps the answer isn't a physical limitation, but a sociological or evolutionary one. Maybe time travel technology is possible, but it is so inconceivably advanced and energy-intensive that it is only achievable by a civilization far more developed than our own. And what happens to a civilization that reaches such an apex? Does it turn inward, exploring the vast landscapes of its own consciousness in virtual realities, rather than bothering with the messy complications of historical tourism? Or does such a civilization inevitably destroy itself with the very power that time travel affords, creating a kind of existential filter that prevents any society from ever existing long enough to become a multi-temporal species? Our timeline might be quiet simply because any civilization that unlocks this ultimate power doesn't use it for long. Another intriguing possibility is that time travelers are here, but their presence is deliberately hidden or indistinguishable from the background noise of history. A truly advanced civilization would likely have a strict code of non-interference, understanding that even the smallest interaction with the past could ripple forward with catastrophic consequences. They would be perfect anthropologists, observing us from behind a veil of secrecy, their technology making them utterly undetectable to our primitive instruments. Their vehicles might not be gleaming chrome machines, but something beyond our comprehension, seamlessly integrated into the fabric of reality. The occasional, uncanny historical mystery, an artifact that seems out of place, a story that feels too advanced for its time, might not be proof of ancient aliens, but the rare, accidental footprint of a time tourist who broke the rules. This leads to a final, mind-expanding thought rooted in the many worlds interpretation. If every journey to the past creates a new branch universe, then time travelers aren't absent from our history, they are absent from this specific branch. Our timeline is just one of an infinite number, and it happens to be one where no one from the future has ever visited. There are countless other versions of Earth where history is constantly being altered and visited by tourists from tomorrow. But we are living on the quiet, undisturbed branch. The anthropic principle applies here too. We can only find ourselves in a timeline that is consistent with our own existence and our observations. A timeline riddled with chaotic temporal meddling might be one that is inherently unstable, unable to support the continuous chain of cause and effect necessary for us to have evolved and to be having this very thought. Our observation of a silent past is what we should expect, because a noisy one would have prevented us from ever being here to listen. But if navigating the quantum realm or the depths of consciousness feels intangible, our next theory offers a pathway firmly rooted in the rapid advancement of technology. Imagine a form of time travel that doesn't require defying the laws of physics, but simply mastering the power of information. This is the concept of digital time travel, a method that sidesteps the perilous paradoxes of physical journeys by proposing that we can recreate the past, not by visiting it, but by rebuilding it from the ground up inside a perfect simulation. The core idea leverages the staggering potential of future computing. Envision a civilization so advanced that it can gather and process an almost inconceivable amount of data about our present era, every email sent, every satellite image captured, every public post on the internet, every digitized birth and death record. With enough computational power and sophisticated AI, this civilization could theoretically create a hyper-realistic simulation of our time. This wouldn't be a simple historical video game. It would be a one-to-one reconstruction of entire cities and their populations, a dynamic model so precise that simulated versions of real people would think, feel, and act with indistinguishable authenticity. A person from this future could then jack into this simulation, not as a passive observer, but as an active participant. They could walk the streets of a recreated 20th century, interact with what appear to be real people, and experience the sights and sounds of a bygone era, all from the safety of a pod in their own time. It would be experiential time travel without the physical risks. This approach elegantly dissolves the most feared time travel paradoxes. The grandfather paradox is neutralized because you're not interacting with your actual ancestor. You're interacting with an incredibly sophisticated program modeled after them. You could not change the real past, only the parameters of the simulation. Any actions you take would ripple through the digital world, but the original, historical timeline would remain untouched. This transforms the time traveler from a potential history wrecker into the ultimate tourist, or perhaps even a historian conducting immersive research. The only limits would be the accuracy of the historical data and the processing power of the computer running the simulation. You could revisit a single day repeatedly, testing different outcomes, or fast forward through decades to witness long-term trends unfold in seconds. However, this digital escape hatch raises profound philosophical questions about reality and meaning. If you cannot tell the difference between the simulation and reality, if it engages all your senses and emotions with perfect fidelity, does the experience lose its value? Is walking through a simulated ancient Rome any less meaningful than walking through the real thing if your brain is convinced it's authentic? This echoes the classic brain in a vat thought experiment, pushing us to question whether all experiences are ultimately just data processed by our consciousness. A digital time traveler might feel the awe of standing in the Colosseum, but they are safe in the knowledge that their actions have no real-world consequences. This safety could render the experience hollow, a knowing theme park ride rather than a genuine encounter with history. The stakes are removed, and without stakes, can we truly claim to have understood the past? Furthermore, this technology introduces a terrifying potential for deception or control. Whoever controls the simulation controls reality for everyone inside it. A future society could use such simulations not for education, but for punishment, trapping consciousness in digital hells. Or they could be used to rewrite history for political purposes, creating propaganda simulations where the past conforms to a specific narrative. The line between historical research and manufactured experience becomes dangerously thin. Would a generation raised in such simulations even care about the objective truth of what happened? Or would the perfectly curated past become their only reality? Digital time travel offers a paradox-free path to the past, but it may come at the cost of divorcing us from the truth, creating a world where the past is not a fixed point to learn from, but a malleable story to be edited and sold. But if we ever do unlock the secrets of temporal navigation, humanity will be faced with a question far more complex than the physics itself. Who gets to use it and how? This brings us to our final mind-bending theory, one that moves from the laboratory into the courtroom and the halls of philosophy. We must consider time travel not just as a technological marvel, but as a potential fundamental right, and with it, the daunting responsibility of building an entire legal and ethical framework to prevent chaos. The core of the debate hinges on a single, monumental idea: access to history. Is the past a common heritage of all humanity, a museum that belongs to everyone equally? Or is it a fragile, non-renewable resource that must be protected from interference at all costs? If we view it as a shared inheritance, then one could argue that every person has a right to witness it firsthand, to walk the streets of ancient Rome, to hear Lincoln deliver the Gettysburg Address, or to simply meet their own ancestors. This would make time travel a fundamental liberty, an extension of the right to explore and to seek knowledge. Denying this access could be seen as the ultimate form of censorship, locking away the truth of our own story behind a veil of technology available only to a privileged few. Yet, the opposing view is terrifyingly practical. Unrestricted access would be a recipe for disaster. The potential for paradox, for historical contamination, or even for simple tourism that alters the delicate course of events is astronomically high. Imagine 1 million visitors descending on a single historical event, each trying to get a better view or take a souvenir. The mere presence of large crowds from the future could itself change the outcome. This isn't just about preventing someone from killing their grandfather. It's about preventing 1,000-time tourists from accidentally introducing a common cold virus to a population with no immunity, or leaving a piece of modern plastic that archaeologists unearth, completely rewriting our understanding of the past. In this light, time travel cannot be a right. It must be the most heavily regulated activity in human history, forbidden to all but a handful of highly trained and rigorously controlled specialists. This leads directly to the concept of temporal law enforcement. We would need a new branch of government, a temporal protection agency, dedicated solely to policing the timeline. Their mission would be twofold. First, to prevent unauthorized travel through strict control of the technology itself, much like how nuclear materials are guarded today. Second, and more difficult, would be to monitor the past for contamination and correct it. This agency would employ historians and detectives to scour historical records for anomalies, artifacts out of place, people saying things they shouldn't know, events that deviate from the established record. Upon finding a discrepancy, they would be authorized to send their own agents back to quietly neutralize the problem, effectively becoming the editors of history, ensuring the book reads as it always has. The ethical dilemmas this creates are profound. Who chooses what the correct timeline is? Would this agency be tasked with preserving a history full of injustice and tragedy because that's what happened? Would they stop a time traveler from attempting to prevent a genocide, arguing that the catastrophic ripple effects could be even worse? This enforces a philosophy of strict determinism, where the timeline is sacred and immutable. Any attempt to make it better is the highest crime. The very existence of such a police force implies that our past is not ours to change, but only to observe, turning history into a zoo where we can look, but we must never, ever feed the animals. Ultimately, the management of time travel would force us to make a defining choice as a species. Do we embrace the chaotic, creative potential of a multiverse where every action spawns a new branch, and thus allow individuals the freedom to explore? Or do we cling to the safety and stability of a single, curated timeline, vesting all power in a central authority to protect our collective past? The answer depends on whether we value individual liberty or collective security more. It's a debate we've had about every powerful technology, from atomic energy to artificial intelligence, but magnified to the absolute extreme. The development of time travel wouldn't just test our engineering prowess. It would be the ultimate test of our wisdom, our ethics, and our ability to govern ourselves when the stakes are nothing less than reality itself. We have journeyed through a labyrinth of possibilities, from the chilling logical loops of the Grandfather paradox to the cosmic scale engineering of Tipler cylinders and Alcubierre drives. We've seen how quantum mechanics offers a universe of multiple realities and particles that seem to dance outside of time, and how Einstein's theories provide a one-way ticket to the future through the relentless pull of gravity and motion. We've grappled with philosophies that suggest our entire timeline is a fixed, four-dimensional block, and technologies that could one day let us simulate, if not visit, the past. What ties all these theories together is their incredible power to dismantle our most basic assumptions. They challenge the very notion of a linear, cause-and-effect reality, forcing us to ask what it truly means to exist, to choose, and to be. They blur the lines between the possible and the impossible, between science and philosophy, and even between the past, present, and future. While a working time machine remains firmly in the realm of theory, The value of this exploration is immeasurable. It pushes the boundaries of physics, inspires new mathematical discoveries, and ultimately expands our understanding of the universe's deepest rules. It is a testament to human curiosity, our innate drive to ask, "What if?" and to follow that question wherever it leads, no matter how strange the destination. So, as we bring this journey to a close, we want to turn the question over to you. Which of these 30 theories bent your mind the most? Did the self-consistent loops of Novikov's principle feel more plausible? Or does the infinite branching of the many worlds interpretation capture your imagination? And if you could step into a time machine tomorrow, where would you go? Would you witness a pivotal moment in history, meet a distant ancestor, or simply travel to next week to check the lottery numbers? Let us know your thoughts and your dreams in the comments below. The conversation about time is far from over, and your perspective is the next chapter. Thank you for exploring the edges of reality with